Well, now it's my pleasure to introduce Professor John Fisher. John is a fellow of this Academy, and he's Deputy Vice-Chancellor of the University of Leeds. He directs the Institute of Medical and Biological Engineering at Leeds University. John's expertise is in total replacement joints, artificial heart valves, and soft tissue biomechanics. A founder of Tissue Regenix, John's track record in innovation includes the Vascutech bioprosthetic heart valve portfolio, which was licensed in 1990, and enjoying 12 years of clinical success. And he is also the designer and inventor of a ceramic on metal hip prosthesis licensed to pay Johnson & Johnson, with 10,000 now implanted in patients worldwide. John is also academic co-founder of Tissue Regenix plc. It's an AIM-listed university spin-out, developing and manufacturing regenerative biological scaffolds. So please give a warm welcome to John.
And I want to talk about some of the most recent research and innovation that we've been doing in the area of biological scaffolds for tissue repair over the last decade. That is a multidisciplinary challenge, and it's really important in the outset to say this isn't the work of an engineer alone, it's the work of an engineer and the biomedical scientists who have led this project over the last decade. We're all required to make disclosures, and these are my disclosures and interests. But the slide actually is very important because it tells you the type and diversity of funding that's supported this research and innovation over well over a decade. And I think it gives a very clear message that to do transformational research and translation, you don't do it over a short period of time, and you don't do it with a limited amount of funding. The three key elements of tissue regeneration involve stem cells, molecules, stimulate cell function, and scaffolds and architecture. And that's the paradigm that's been described for 20 years. The approach that we've been taking is to say that actually, is it possible to stimulate tissue regeneration and repair simply by using biological scaffolds, which recruit the patient's own stem cells to stimulate the repair and regeneration process. Why is that so important? That if you recruit the patient's own stem cells, then the medical technology can be translated as a Class 3 medical device. The route to market and indeed the development costs are at least 10 times less, tenfold less than a cell therapy. And in today's climate where economics and risk are the primary factors into consideration of successful translation, that's really important in the approach. So why are we addressing this, and what are the clinical and market needs? We've already heard about the ageing population. We use the term 50 active years after 50. If you are 50 years old today, you've got a high probability of living well into your 90s. If you were born this year, it's very probable that you will live into your hundreds. Parts of our system, parts of our body are not designed to last 100 years. We start to degenerate in early middle age. Many of us in the audience probably know that already. It's a market that's growing dramatically. In Asia, it's growing at 35% per annum, 10% in the Western world. I was in Singapore recently. 27% of the manufacturing in Singapore is now in medical technology. And there's a global need for reduction in the unit cost of healthcare. I was at a meeting this morning with the head of the UK Civil Service, and he was saying the cost of the ageing population is right up there on the current agenda in terms of government spending. And if you feel all that is not important to you, let me say 10% of you in this room today will need some form of intervention that I'm going to describe at some point in your lifetime. The challenge we have is, of course, we don't know which 10%. And that's possibly where the future of stratified medicine comes in. Let me describe a very simple concept of a functional biological scaffold for tissue regeneration. The technology starts with tissue, whether that be from human source as a donor human tissue or from an animal source. And the process is very simple. We remove the cells and the immunogenic components of the tissue with patented bioprocesses. And then we have a scaffold that is free of cells. And then that scaffold, when it's implanted in the patient, can regenerate with the patient's own stem cells to form repair and regenerative tissue. Many things in life, many important things in life are simple. The key is to be able to remove the immunogenic components of the tissue while retaining the tissue scaffold. Why is this important? Well, the characteristics of these functional biological scaffolds, they provide a biologically and immunologically compatible environment for tissue repair, which attracts the patient's own cells. But it is, most importantly, an acellular therapy. That means it can be translated to the patients at much lower costs and at much lower risk than a cellular therapy. So it provides a low-cost regenerative solution. Most importantly, it replicates the tissue-specific multi-scale architecture and biomechanical function. And that's important because that scaffold will convert and translate the forces and stresses acting on the scaffold to microscale level strains, which will stimulate the cells to differentiate down the correct pathway. So the tissue or the scaffold architecture is critical for the mechanical transduction of cell differentiation. This is a slide I use to talk to biologists about this process. But I don't apologise for presenting it to you here. We can all, as engineers, recognise the macroscale forces and biomechanics. So if the tissue specimen on the left-hand side there is a piece of ligament, for example, it will transmit forces and extend characteristically in the form of a ligamentous tissue. And what's really important, if you're going to replace that tissue with a biological scaffold, is the scaffold behaves in a very similar way to the tissue it's replacing, both at a macroscopic level in terms of the extension and force curves which I've shown there, but equally important at the cellular level. So the scaffold architecture has to be able to transmit the forces being applied on a macro scale to a three-dimensional strain field acting on the cells to drive the cells down the correct differentiation pathway. And only tissue-specific scaffolds can do that. So scaffold, you need to do that in a ligament is different from what you need in a blood vessel, is different from what you need in a piece of cartilage, is different from what you need in a heart valve. Every one of these scaffolds has to be specific to the tissue that it's repairing. So why not start with nature's scaffold, which is a tissue itself that it's going to repair? So the process is simple. We start with either an animal tissue or a human tissue. There are two families of products in these scaffolds, ones that are derived from human tissue and one from animal tissue. You remove the cells and the immunogenic components, you retain the extracellular matrix, you retain the function and biomechanical properties, and when you implant it in the patient, it has the potential, and we have evidence that it regenerates with the patient's own cells. This is details of one bioprocess that we need to create these sorts of scaffolds, starting in this case with a scaffold for a heart valve. The skills we need are on the right-hand side. They involve engineering skills, they involve biomedical skills, and of course they involve other skills in terms of clinical translation. Preclinical testing of devices is critically important alongside clinical trials. If we're going to improve safety and effectiveness of devices, we have to put more engineering effort into the preclinical evaluation of them before they go into the clinical trials. We have to understand how those devices, how those scaffolds interact with the complex environment in the body and the variation in that environment that you see from patient to patient. I just want to show you this slide because as well as developing the scaffold technology, we've had to develop new technologies to preclinically evaluate the function of the scaffold and the devices that we're putting into the body. This is a simulator for a knee. We've had to develop similar systems for the hip, for blood vessels, for heart valves, for ligaments. So, what best way of describing the technology and the research and innovation from the research laboratory to the patient, to the commercial product, is simply showing you some case studies. This is the product portfolio from the earliest product, which was heart valve scaffolds, to the current research products involving bone and soft tissue, which we're currently working on. There are in fact three families of products. One involves thin membrane tissues, the heart valves, vascular patches. The second one involves musculoskeletal soft tissues, ligaments, tendon. And the third one involves more complex structures, which involve bone and soft tissue complexes. Each of them poses its own challenge for this type of technology development. But it is truly a platform technology, a technology that's got many applications. So, an example of a cardiac valve. So, on the left-hand side there, we see the source material for the scaffold, the native material, the acellular scaffold produced from that. On the right-hand side, we see the type of biomechanical function testing that we need to do to evaluate that scaffold. At the bottom of the slide, you may not be able to see it, you see the results of large animal studies, which are preclinical studies. This was our first technology. It was successfully translated with collaborators in Brazil, and they now have successes in both pulmonary valve repair in young people as well as aortic valve repair in young people. Why is this important? Well, it's an unmet clinical need. If you need a heart valve repair and you're a young adult or even a teenager, a single operation will not last you your lifetime. This type of regenerative technology has the ability to repair or replace valves in young people with regenerative solutions that will grow with that patient throughout their lifetime. So that's the first product. The first product involving animal tissue was a vascular patch. This is a simple patch to repair blood vessels after surgery. So the surgeon might go in and remove the plaque that blocks the blood vessel and then needs to close it and repair it. So this is a biological scaffold for vascular repair. This slide just shows you the scaffold and the sorts of physical or mechanical properties the scaffold has to exhibit. This shows the results of large animal studies which have to be undertaken before clinical trials, showing the regenerative capacity of the patch. This shows some repopulation of the scaffold. In this case, the cells that you see are the cells of the animal that received the scaffold. So these are the cells that are repairing with the scaffold. And this is the clinical product, the first clinical product produced by Tissue Regenics, which is a university spin-out. It's now an AIM-listed company, and I think it's had over £30 million of private sector investment into the company to develop this portfolio of technologies. Similar type of approach. This is technology that hasn't reached the patient yet, but evolving from a vascular patch to a whole vascular graft. Major challenges with diseases such as diabetes and the need for vascular repair. This is currently work that's going on in the development phase and working through large animal studies. Just a little bit now about a second category of scaffolds for musculoskeletal repair, particularly in terms of tissues in the bones and joints. This is a slide of a decellularized meniscus. So on the left-hand side is a scaffold for meniscus repair that can be cut to shape by the surgeon, and that's a biological scaffold that has the same properties as the natural meniscus tissue, and it will repopulate once it's been implanted in the patient. This is just some mechanical characterization that compares the properties of the decellularized scaffold with the properties of the fresh material. And this is a product that's currently with Tissue Regenix undergoing commercial product development. Ligament replacement, another musculoskeletal scaffold, a biological scaffold. In this case, we're starting with tissue from an animal, decellularizing it, retaining the mechanical properties and the multi-scale architecture. Again, a product that's currently in the development pipeline with Tissue Regenix. And this is just some laboratory work that shows that these musculoskeletal scaffolds will also regenerate and repopulate with cells. So this is an in vitro laboratory cell culture system where the ligament scaffold sits on a bioreactor where the tissue is being stretched. We seed it with cells on the surface. 3 weeks later, we see the cells penetrating into the scaffold, and the pictures on the right-hand side provide the biological evidence of that. I only put this slide up to reinforce the point of mechanical transduction. If you do this experiment and you do not apply biomechanical stress and strain to the scaffold, you do not get the repopulation and you do not get the cells differentiating down the right pathway. Very important evidence of the role of mechanics and mechanical transduction in tissue regeneration. So this is my final slide. It's just showing you a picture of that product portfolio of translation from work we started in the research laboratory 10 years ago in heart valves to work that we're currently doing in the EPSRC and Wellcome Trust funded centre on bone and soft tissue at the bottom. To emphasise, there are 2 very different translation pathways. If we start with a scaffold which involves human tissue, we do it through the National Health Service, National Blood and Tissue Service, who are investing in this technology. If we do it with scaffolds derived from animal tissue, they become medical devices and are CE marked and follow a different regulatory pathway. Thank you for your attention.
Well, thank you very much indeed, Professor Fisher. And now a couple of quick questions. Yes, sir.
Hello, Pankaj, University of Edinburgh. This is an extremely, I'm aware of your work, extremely impressive piece of the work you've done. As a modeler, I always get confused when we say tissue differentiates or, and you talked about mechanotransduction, as to what kind of environment different tissues require in terms of mechanotransduction. For example, bone, does it require strain energy density, which a lot of modelers use, or does it require tensile strains, compressive strains, hydrostatic strains? I mean, that's the sort of information I don't normally get as a modeler.
Okay, so I think it's best answered by just giving you 2 simple examples. That if you see the scaffold that is designed for ligamentous repair, and you seed it with stem cells, by applying the appropriate ligamentous force and strain field, you can differentiate those cells into tenocytes. Conversely, in a bioreactor of a blood vessel, I apply a biaxial strain field to an appropriate biological scaffold, I can differentiate those same cells down a smooth muscle cell pathway. So that's telling you that you need the appropriate 3-dimensional strain field acting on the cells. And to achieve that, you need the appropriate architecture, tissue-specific architecture in the biological scaffold to deliver that cell differentiation.
One more question? Yes, sir.
Jack Chen from the Chinese University of Hong Kong. You mentioned exciting work. Thanks for sharing with us. It's about the biological side. You remove the cell and together with it, the growth factors, the cytokines, the vasculature. And so now you're actually providing all these mechanical environment and micromechanical. But how about those biological? The vascular side, the growth factors, the cytokines, and all that?
Sure. And the scaffold is the starting point. These scaffolds can in the future be used with other molecules that are already regulatory approved. We have plans to look at projects in the future bringing not just autologous stem cells but other molecules to bear on the scaffold. I would say, being an engineer, that I like to start with getting the biomechanical environment correct in the first place, because I believe that's a prerequisite. If you do not have that right scaffold architecture there, you will not get your cells to differentiate down the right pathway in whatever molecules that you choose to put in. But I entirely accept it's a vehicle for delivery of other factors, including growth factors, which can help to stimulate the repair processes in the future.
Well, very impressive work, I think you must all agree. So thank you very much indeed.